Did you know that every 12 months, the world's vehicle fleet consumes and discards more than 250 million tires? Whether for commuting, taking scenic routes, or burning rubber in extreme maneuvers, modern vehicles rely on 4 black rings that at first glance seem as ordinary as they are indispensable. Yet behind their robust appearance hides the fragility of an essential ingredient, a white, milky, sticky fluid botanists call latex. After a chain of processes that blends agriculture, chemistry, and high-end engineering, that latex becomes the tires supporting cars, trucks, and motorcycles all over the planet. Although the wheel has existed for millennia, the idea of wrapping its perimeter in rubber is relatively recent. In the early years of the 18th century, some artisans experimented with natural resins to protect the wooden and iron rims that dominated the roads of the time. Those first trials were unpromising. The rubber wore quickly and cracked under extreme temperatures. The situation changed radically in 1839, when the American Charles Goodyear, after countless tests and a famous accident in which a mixture fell onto a hot stove, discovered vulcanization. By combining raw rubber with sulfur and applying heat and pressure, Goodyear achieved a more stable molecular structure, elastic and resistant to abrasion. Thus, the modern tire was born. Today's tire manufacturing brings together 2 major families of elastomers whose combination is essential for balancing performance and durability. Natural rubber, extracted from the latex of Hevea brasiliensis, offers extraordinary elasticity, high recovery after deformation, and excellent grip on varied surfaces, absorbing impacts and ensuring firm contact with the pavement, especially at low temperatures. Working alongside it is synthetic rubber, produced by polymerizing petroleum derivatives such as butadiene, styrene butadiene, and synthetic isoprene. This family supplies superior chemical resistance, crucial against fuels, oils, and ozone, and greater batch-to-batch uniformity, which simplifies large-scale quality control. In an average tire, both polymer sources coexist in proportions that usually range between 30 and 50% each, though the exact formula changes with tire type and desired performance, sport driving, heavy load, winter use, and so on. Into that bicomponent matrix go additives that multiply performance. Carbon black to boost abrasion resistance and dissipate heat. Precipitated silica to improve wet traction and reduce rolling resistance. Metal oxides such as zinc oxide, which catalyzes vulcanization. And oils, resins, and waxes that act as plasticizers, antioxidants, or ultraviolet shields. The result is a compound whose mechanical, thermal, and chemical properties are finely tuned to endure millions of flex cycles, extreme temperatures, and shifting loads throughout the tire's service life. Rubber plantations thrive in equatorial belts of hot, very humid climate. India, Thailand, Indonesia, and Vietnam supply a large share of global production. When a tree reaches maturity between 6 and 7 years after planting, workers make a shallow helical cut in the bark. The incision must pierce just 2 millimeters, enough for latex to flow without harming the tree's vascular tissue. Drop by drop, the white sap slips into a small aluminum or ceramic cup. Each tapping yields little. Thousands of trees are required to feed an industrial plant. To keep the latex from coagulating prematurely, a measure of ammonia is poured into the collection buckets. The alkaline compound acts as a preservative, stabilizing the suspended rubber particles. Once full, the receptacles are moved to storage, where the latex rests in sealed tanks for about 10 hours. Time for a natural pre-curing phase that thickens the dispersion before controlled solidification. After resting, the mixture still contains about 60% water. To expel much of that liquid, the latex passes through a train of corrugated rollers functioning like giant pasta machines. Successive pressing compacts the material into thin sheets of uniform thickness. Yet the rubber remains moisture-laden, so the sheets are hung in drying galleries fired by wood and streams of hot air. 3 days later, what was a viscous fluid has become flexible planks, light amber in color, bearing the sweet aroma of tropical sap. Once the natural rubber reaches preliminary consistency, it is compressed into bales of between 35 and 50 kilograms for easier handling. These blocks travel on flatbed lorries or inside ventilated shipping containers covered with waterproof tarpaulins that protect them from tropical rain and excess sunlight. In the same convoy, synthetic rubber arrives in densely packed bales from petrochemical complexes. At the industrial site, both elastomer types enter climate-controlled warehouses where humidity stays below 60% and temperature around 18 degrees Celsius, preventing surface crystallization and slowing oxidative degradation. Bales rest on raised pallets with clear aisles for electric forklifts that feed the production line according to the daily schedule. Before any lot enters the mixer, lab tests verify ash content, Mooney viscosity, and impurity percentage. Only then is it cleared for compounding. The factory's heart is the mixing hall, a noisy space filled with Banbury mixers, closed kneaders the size of school buses, and 2 roll mills. Technicians load different recipes depending on the tire section: inner liner, sidewalls, belts, tread, shoulders, or bead. In each mixer go rubber, carbon black, sulfur, zinc oxide, antioxidants, chopped textile fibers, and plasticizing oils. Friction and heat blend the batch until it reaches the right viscosity. In barely 2 minutes, a shiny black blanket emerges, still malleable, then is rolled into continuous sheets and stored in coils. Rubber alone is too soft to contain inflation pressure or withstand roadway impacts, so it is combined with polyester, rayon, or aramid fabrics that add tensile strength. A calendar, its heated rollers coated with rubber, impregnates both sides of the fabric to create carcass plies. Fabric thickness and density vary with tire category: touring, high performance, off-road, and so forth. Simultaneously, high-strength steel wires are grouped into cords, rubber-coated and formed into belts that stabilize the tread and prevent deformation at high speeds. Among the least visible yet most critical components is the bead. Circular hoops made of braided high-tensile steel filaments coated with rubber to bind with the carcass. During assembly, the bead is the primary contact point between tire and rim. When inflated, internal pressure forces these hoops against the wheel's metal flange, creating an airtight seal. Bead quality is vital. If the wires lack tensile strength or perfect sizing, inflation pressure, which can exceed 5 atmospheres in lorries or high-performance vehicles, might unseat the tire, jeopardizing stability and raising the risk of sudden loss of control. With all subcomponents ready, they are mounted on a building machine resembling a horizontal lathe. On an expandable metal drum, the operator first lays the inner liner, a butyl rubber layer almost impermeable to air that replaces old tubes. Then, the carcass ply positions the beads on both sides and folds the fabric edge around them. Steel belts wrap over the carcass, and finally the tread with its shoulders is applied. A light puff of compressed air helps bond the layers. The result, called a green tire, has no tread pattern yet and has not undergone its irreversible chemical reaction. The road contact portion needs a special recipe. 3 distinct compounds, 1 central for wear resistance and 2 lateral for grip and heat dispersal, are extruded simultaneously through a steel die. The profile carries longitudinal grooves for orientation and section identification, while inked rollers paint colored stripes serving as internal codes during quality checks. The green tire then enters a steel mold split like a giant waffle iron. Inside sits a flexible bladder of water and steam. When the mold closes, pressure, which can top 20 atmospheres, and temperature around 180 degrees Celsius, activate the sulfur and create sulfur bridges between polymer chains. After roughly 15 minutes, the tread gains its final pattern, and all layers bond chemically into a single elastic, solid, highly durable piece. Excess rubber, or flash, is trimmed with circular knives. Each tire undergoes visual and mechanical inspections: dynamic balancing, radial uniformity scanning, X-rays for hidden air pockets, and leak tests. Only those that pass enter the marking and storage area, where lasers or presses engrave sidewalls with production codes, size, load index, speed symbol, and regulatory data. Having completed a chain of operations combining robotic controls, precision chemistry, and human skill, the finished tire rests on pallets tagged for traceability. From there, it begins a logistical journey that may involve rail, sea, and long-haul lorries before reaching distribution centers, dealers, or service shops. Units are kept in ventilated spaces away from direct light to preserve elasticity and avoid premature deformation. When finally fitted on the rim, the steel bead seals against the metal flange, and the airtight inner chamber receives air at the pressure the maker recommends. Then the tire enters its true proving ground, the open road. It must provide dry grip, evacuate water in rain, cushion bumps, hold stable in corners, and keep noise within comfort regulations. The tread pattern, born of multi-compound extrusion, channels friction heat, lowers aquaplaning risk, and distributes wear to extend service life. Every emergency stop, urban slalom, or long motorway stretch on scorching asphalt showcases the textile reinforcements and steel belts embedded in the carcass. Meanwhile, pressure and temperature sensors in modern wheels send data that engineers study to craft ever more efficient and sustainable compounds. Thus, the tire becomes an information node fueling innovation. The journey that began with a millimetric cut in the bark of a Hevea brasiliensis and passed through giant mixers and molds at 180 degrees Celsius, completes itself each time a vehicle brakes with precision or corners with poise, reminding us that contemporary mobility rests on a complex convergence of science, industry, and global logistics.